All right, so now we're going to talk about the inverse of a matrix. So these definitions I need you to get comfortable with. So singular means it's not invertible. Non-singular means it is invertible. I know I would have made them different too, but oh well, that's just the way it is. Okay, so non-singular means it is invertible. All right, so if I have a 2 by 2 matrix, first thing I need to make sure is that AD minus BC does not equal 0. And if you remember, that's called the determinant. So it's this times this, subtract this times this. So as long as that AD minus BC is not 0, then the matrix is invertible. And the matrix is 1 over that number. And then let's check out what's happening in here. So the A and the D, these two get switched, and the C and the B, you get a negative sign times them. Just need to memorize this. All right, so here we go. So here I have a system, and yes, you could always augment and solve, but let's do it a different way. Let's use the inverse to solve it. So if I have, excuse me, AX equal B, right? So the matrix A, and here's B. So AX equal B. What I'm going to do is I'm going to be finding A inverse, and I'll be multiplying on the left on both sides. So then I'll get X is equal to, right, the vector X will equal A inverse B. All right. So let's go find, well, here's my A. You know how to pick that out. So finding the inverse is 1 over 32 minus 30. So that's the number in front. That's the determinant. I switch the things on the diagonal. I take the opposite on these two diagonals. And I'm going to take the time to multiply the number in. So multiply the number 1/2 in. All right. So to solve, to find what X is equal to, I'm going to take the A inverse times the B. So A inverse matrix times the B gives me 7, -9. This is the exact same answer I would get from the augmented matrix. But we're going to find out that sometimes the inverse is going to be, it's going to be helpful. All right, if it's invertible, which means non-singular, then for every B in Rn, this does have a solution, and the unique solution is X equal A inverse B. All right, so if A is invertible, then just more facts you need to know. If A is invertible or non-singular, then A inverse is invertible. And A inverse inverses A. So it's kind of like what we just did with transpose, right? So we had A transpose is A. Here we have A inverse is A. And if A is invertible, then A inverse is invertible. That's going to be important. All right, if I have A and B and they're square, have to be square in order to be invertible, then they're non-singular, which means invertible, then their product is invertible. That's a big one. So if A and B are invertible, their product is also invertible. And the inverse of AB, so if I want to find AB inverse, it's the inverses, it's the product of the inverses, but in reverse order. That also sounds like transpose, doesn't it? Switch the order and take the inverse. Okay. If I know A is invertible, then so is A transpose, meaning A transpose is invertible. So if A transpose, the inverse of A transpose, I should say, the inverse of A transpose will be A inverse transpose. So the inverse of A transpose, you can switch the order of these things. Okay, just good fat things you need to know. If I know that A is non-singular, invertible, that gives us the information, if and only if, A is row equivalent to IN. That means if I did RREF with my matrix A, I would get to the identity matrix. And if it's non-singular or invertible, that means the determinant is not 0.